Hello, welcome to the second part of my lecture. So the second part is devoted to a description of the models that attempt to reconstruct how the solar system formed and evolved. I remind you that in this talk, I will make reference to many observational constraints, and these observational constraints are discussed quite extensively in the first part of my lecture, which is recorded in another video. So when a star forms, it is surrounded by a disk, a protoplanetary disk or circumstellar disk made of gas and dust. And the existence of this disk was predicted on the basis of a fundamental law of physics, the conservation of angular momentum by Laplace. And today, this is not a model anymore. Wherever we observe young stars, we see that these young stars are indeed surrounded by circumstellar disks. So the circumstellar disk is made of gas and dust, and the dust, because it's not in vacuum, but it feels friction from the gas, undergoes two kinds of movements. It sediments towards the midplane of the disk, and it migrates radially towards the central star. The speed at which the dust does so depends on its size. If the size is very small, the speed, for instance, at which it migrates towards the sun is very weak because the dust is strongly coupled with the gas, so it tends to move with the gas, which is simply orbiting the star while not going anywhere. And if the dust is very big, so kilometers in size, so it's not dust, it's planetesimals, also the friction that it feels from the gas is very weak, and therefore the migration will be very slow. But there is an intermediate size at which the friction time is comparable to the orbital time scale, for which this radial migration towards the star is pretty fast and can actually remove the particle in tens of thousands of years. And this curve, for instance, has been computed by White and Schilling for a distance of 30 U, but one can do the same kind of calculation anywhere in the disk and always find this shaped curve. And the same curves applies to sedimentation. If the dust is very small, the sedimentation is very slow. So the dust floats in the gas, in the atmosphere of the disk. If the particle is big, it's a planetesimal, what happens is that the vertical motion of the particle or the body is an oscillation around the midplane. And this oscillation is slowly damped towards the midplane. And if the dust has this intermediate size where the friction time scale is comparable to the orbital time scale, then we have a fast sedimentation on the midplane. So everything depends on how fast, how big the dust can grow. And so to answer this question, laboratory experiments have been conducted, particularly in Germany, where this activity has been very fertile. And initially the dust is very small because the dust that comes from the interstellar medium or the monomers that condense when the gas in the circumstellar disk starts to cool. So nanometer in size or a few fraction of a micrometer in size. These particles can stick together quite efficiently thanks to electrostatic forces forming fractal aggregates. And then various fractal aggregates can join and stick to each other again by these electrostatic forces, forming fractal aggregates that are bigger and bigger and more compact. But at some point, if the collision energy becomes too big, which means big fractal aggregates or big relative collisional velocity, then these aggregates starts to lose chips and so don't grow anymore. And if the collisional energy is even bigger, then the collision can be catastrophic and the aggregates are dispersed in the individual monomers again. So with an estimate of the typical collisional velocity in the disk, which are due to the different sizes of the aggregates, which induce drifts at different speeds, but also the turbulent stirring inside of the nebula, it is estimated that in the part of the disk where only silicates are solid, probably particles can difficultly grow beyond the size of about a millimeter. And once they reach this size, the aggregates start to bounce off each other before starting to lose chips and stop growing. Maybe for icy particles, in the cold disk where water in the form of ice then the particles can grow bigger because ice is more sticky than silicates, particularly when it's relatively warm, so close to the sublimating temperature. And in this case, one can envision that the dust grows to a size, to a pebble size particles with a size of the order of a centimeter or of a decimeter. So one can wonder whether this is correct or it's just a problem in our understanding of particle sticking. And so we can break open a meteorite to see what is the size distribution of its constituents. So this is a slice of an ordinary chondrite, and what you see here are the main constituent of the chondrite, which are the chondrules. And chondrules are typically particles of the order of a millimeter in size, even a little bit smaller. It's very difficult to find in the meteorite something significantly bigger. There are sometimes centimeter size CIs, nothing bigger than that. Of course, chondrules could stick with each other to form chondrule aggregates, which are bigger than the individual chondrule. And indeed, we do see compound chondrules or chondrule clusters in meteorites, but these are relatively rare. Most of the particles are individual and millimeter in size. So probably a planetesimal, at least in the inner part of the disk where water is not in the form of ice, have to form starting from particles which are relatively small. So how can we go from millimeter-sized particles to objects which are macroscopic, several kilometers in size, as an intermediate step to obtain planets, bodies that are called planetesimals? This has been a very difficult problem that the community has struggled with for many, many years, if not decades. And there has been recently a real breakthrough. So it has been understood by studying the evolution of these particles in the disk with the feedback of particles in the disk, that there are hydrodynamical processes that can clump the particles. And in particular, there are two such processes which are very important. They're actually two different sides of the same process, really. One is related to the sedimentation of the particles towards the midplane, which triggers an instability called the Kelvin-Helmholtz instability. And the other one is due to the radial drift of the particles, which can trigger another instability called the streaming instability. Here, I will take these simulations from Johansen et al. 2006 from the Kelvin-Helmholtz instability to illustrate what's going on, because I think this simulation is a little bit more clear than those of concerning the streaming instability. So what are we seeing here? So this is a cut of the disk at a given distance from the sun. So the vertical direction is the vertical direction of the disk, 0 indicating the midplane. And this is the azimuthal direction. So this is the direction that goes around the star. And the colors here highlight the density of dust. There is gas also, but the colors illustrate only the density of dust. So let's see what happens. At the beginning, the dust forms a band around the midplane, and then the dust starts to sediment towards the midplane. But once it sediments enough, so the colors you see change, this triggers an instability, the Kelvin-Helmholtz instability. So the dust cannot sediment indefinitely. This instability generates turbulence. The big discovery has been that once turbulence is generated, the dust tends to cluster in the turbulent structures. And so locally, one can obtain clumps which can have a very significantly high density. So locally, it's not a band around the midplane, it's really physical clusters in 3D, and these clusters of particles can be very, very dense. These are snapshots from another simulation of the streaming instability. So this process has been now studied by many, many groups with more and more sophisticated hydrodynamical simulations with increasing numerical resolutions. And these plots are taken from the work of Lee et al. And then used in these works by Nesvorny et al. So what are we seeing here? So this is another view of the disk, now top down. So each panel is actually a representation of what's going on the midplane. So this is the radial direction, the sun being in this direction, and this is the azimuthal direction, that is the direction of disk rotation. And again, the colors show the ratio between the density of the particles and the mean initial density of the particles, so the particle gas ratio, if you want. So at the beginning, as you can see, the disk is just very mild inhomogeneities, but as the time goes on, after 2 orbits, 4 orbits, these inhomogeneities grow, and you start to see clumps where dust is denser and denser. And eventually these clumps become so dense that they become self-gravitating. And when it's so, they are highlighted by these white circles. And a very recent analysis, numerical and analytical analysis by Clark and Schreiber show that the mass in these self-gravitating clumps is typically comparable to the mass of a planetesimal of 100 kilometers. So when these self-gravitating clumps slowly collapse due to their self-gravity, and all these dispersed particles formed a solid planetesimal. The typical size of this planetesimal is 100 kilometers, plus or minus, of course, some uncertainty. So the size distribution is typically a Gaussian distribution around 100 kilometers. And this 100 kilometer privileged size, indeed, we can see it in the size distribution of Kuiper belt objects and in the asteroid belt. Indeed, most of the mass in these belts is carried by planetesimals of 100 kilometers if we exclude the very big ones, which probably started to grow towards the planetary regime. So there is now a very strong argument in favor of this idea that planetesimals form by the collapse, gravitational collapse of particles. And this is reproducing the properties of binary planetesimals that we still see today in the Kuiper belt, in particular in the cold population of the Kuiper belt. When the clump of particles becomes self-gravitating, it typically has some kind of rotation. So when it contracts to form a planetesimal, it has an angular momentum that it has to conserve. So the way to have a collapse by conserving angular momentum is to avoid forming a single object, but to form a number of objects, and typically 2 of them orbit each other, forming a binary planetesimals with roughly equal size objects. Indeed, by the analysis of the clumps produced by the streaming instability, the main properties of the binary objects we see in the Kuiper belt have been reproduced, in particular by Nesvorny, Uding, and Richardson already 10 years ago. So for instance, the semi-major axis of the binary versus the eccentricity of the binary is very well reproduced. The triangles show what is observed in Kuiper belt binaries, and the color dots is what is obtained in simulations, the colors referring to different simulations, but it is not very important. Another important observation, as I said, is that these binaries are made of 2 components which roughly have the same size. The difference in size is very small. The difference in magnitude is a proxy of the difference in size. And here again, you see the typical difference in magnitude of the real binaries observed in the Kuiper belt, and the color dots show the difference in magnitude predicted by the model. But the most striking result came only recently in this paper in Nature, where it has been shown that the orientation of the angular momentum vector in these self-gravitating clumps formed by the streaming instability reproduces the statistics of inclination of the orbital plane of the Kuiper belt binaries. So the dashed line here shows the cumulative distribution of the inclination of the Kuiper belt binaries. As you can see, 80% of the Kuiper belt binaries are prograde, so their mutual inclinations relative to the plane of the solar system is less than 90 degrees, and about 20% are retrograde. And the solid curve is the statistics of the distribution of the angular momentum vector in the self-gravitating clump, which in the end becomes the normal of the orbital plane of the binary once the clump contracts to form the binary planetesimals. So the 2 match really very well. And this is the only model of formation of Kuiper belt binaries that is able to reproduce these statistics of prograde versus retrograde binary. So this is a very strong argument in favor of the fact that planetesimals do form from the contraction of self-gravitating clumps of particles, clumps that form due to various hydrodynamical instabilities and particle-gas interactions. So everything is solved now? Well, not really, because it has been shown that in order to trigger these instabilities, one has to start with a disk that has a relatively high dust to gas ratio integrated vertically. So for instance, this diagram taken from a recent paper by Yang et al. Shows what is the dust-to-gas ratio Z, the surface density ratio that is needed in order to trigger the streaming instability as a function of this parameter, which is called the Stokes number. The Stokes number is the ratio between the friction time scale of the particles and the orbital period. So in the outer part of the disk, where maybe the grains can grow to a few centimeters in size, the typical Stokes number, say 20 U of these centimeter-sized particles, is almost unity. In the inner part of the disk, say 2 U, a millimeter-sized particles like a chondrule has a much smaller Stokes number because its stopping time is much, much shorter than the orbital period. And the typical Stokes number is of order of 10 to minus 3. So here you see that as a function of the Stokes number, you need that Z is of a few percent in order for the streaming instability to operate. This part of the parameter space highlighted in green, whereas here in red, the streaming instability cannot be triggered because the dust-to-gas ratio is too small. And the typical dust-to-gas ratio initially in the protoplanetary disk should be equal to the metallicity of the sun, so the order of 10 to minus 2. So you can see with 10 to minus 2, you don't do anything. Streaming instability is not operational. Planetesimal self-gravitating clumps and planetesimal should never form. So you need to increase this to at least 2% if you have the best Stokes parameter, and even to 3-4% if you are working with chondrules in the inner solar system. So before triggering the streaming instability, it's needed that the dust piles up somewhere in the disk to enhance locally the dust-to-gas ratio, and only then the streaming instability can operate. Now, so far, the only place in the disk where it's understood that this enrichment in dust can happen and triggering then the streaming instability is at the snow line. What is the snow line? Is the location of the disk where water becomes solid. Inside of the snow line, the disk is too hot, water is vapor. Outside, water is solid. So there is, if the disk density declines with distance, then the solid distribution is expected to have a step here at the snow line, because inside you only have silicates in refractory elements in solid form, and outside you have the refractory elements, of course, but also the ice in solid form, which increases the amount of solid material available by about a factor of 2. So this is a cartoon taken from this paper by Drevkovsky and Alibert 2017 showing what happens. So inward of the snow line, you have only silicate particles, and water is in the form, which are depicted in brown, and water is in the form of gas, which is this blue band. Outside of the snow line, you have both silicate particles and ice particles. What is conceived is that the silicate and ice particles clump together to form an aggregate where the silicate particles are entrained in some icy matrix. So you have pebbles that are made of refractory material and ice. And inside you only have refractory dust in a gas reaching water vapor. And particles drift towards the star. These particles, as I said before, are expected to be bigger than these, so they are expected to migrate faster than those. Anyway, when these particles migrate and they reach the snow line, they pass inwards of the snow line, and then the ice in the pebble sublimates. So, and only the grains, the silicate grains, continue their migration towards the star. So this enhances, this creates, first of all, a traffic jam, because these particles are drifting faster than these. So as these particles sublimate the ice and become smaller, they slow down. So it's like a traffic jam of cars on the highway. When there is a slowdown in cars, the cars come together, and there is a traffic jam. In addition, there is a bump in water vapor here, because it's due to all the ice that sublimates and the condensation line. And because the gas diffuses, some of this vapor will go outwards, will go beyond the snow line and condense again. And these two processes together create a bump in the dust distribution located in the snow line, in particular beyond the snow line, because of this recondensation of water vapor. So locally, one can have an enhancement of the dust-to-gas ratio that is large enough to trigger the streaming instability and convert the particles into planetesimals. However, it's clear for what I presented in the first part of my lecture that it makes no sense that planetesimals form at a unique location in the protoplanetary disk. We have seen that the cosmochemical evidence is that the early planetesimals in the solar system form at least at two distinct locations, because we have iron meteorites, which come from planetesimals that form early enough to differentiate, that belong to both the carbonaceous chondritic group and the non-carbonaceous chondritic group. And so with completely different isotopic distributions. And if all planetesimals formed in the same place, this would not be possible. For those who know the literature in this topic a little bit, in 2016, Drazkowska et al. Claimed to understand how planetesimals could form, how dust could pile up, and then planetesimal could form a 1AU. But in that work, they used planetesimals that are too big, that were too big compared to what is now understood from studies of particle coagulation and fragmentation. So this result about dust pile up at 1AU by Drazkowska et al. 2016 was then dismissed by Drazkowska and Aliber in 2017. So far, it's fair to say that it's robust, that we have a robust understanding of planetesimal formation at the snow line, but only at the snow line. And this doesn't work. So we need to work further in order to understand early planetesimal formation, at least at two sites in the protoplanetary disk, so that first planetesimals form from different materials with different isotopic properties. Moreover, there is another problem, is that, as I showed in the first part of my lecture, there are two generations of planetesimals. There are the early planetesimals that form at two sites, but there are also late planetesimals that formed a couple of million years later. And how could they form? According to our best understanding, again, I'm using these plots from Drazkowska and Aliber 2017, the dust to gas ratio decreases with time. Look at that. So this is the distribution with respect to distance from the star of the gas and the dust. Initially, the dust is about 1% of the gas density, because this is the metallicity of the sun. Initially, on very short time scale, because the dust moves inwards, and it moves inwards, the Stokes number decreases and then slows down, the disk gets depleted of dust in the outer part, but the dust concentrates in the inner part. And so the dust to gas ratio increases. It's not 1% anymore, it can grow maybe to a few percent, in particular close to the snow line, because of the effect I described before. The dust to gas ratio can approach unity. And so locally, one, as I said before, can trigger steaming instability, forming planetesimals around the snow line. The snow line is moving around, so this planetesimal distribution spans a region where the snow line was propagated. But then, already at 500,000 years, as you can see, once these planetesimals, the snow lines are formed, the dust to gas ratio becomes small, very small. And now it's not 1% as it was at the beginning, which is not enough to form planetesimals. It's much less. It's 1 in 1,000 or something like that. So the magic moment of planetesimal formation is gone, and nothing else should form again. And this is not what we see in the meteorite collection. We see the chondrites formed 2-3 million years. So how is that possible? Well, somehow we need to preserve the dust. So one idea is that there are obstacles to dust migration. And indeed, when we look at protoplanetary disks, like this fantastic image of HL Tau by the ALMA instrument, we see rings. And rings are due to dust that is either permanently trapped at a given location, or at least is slowed down at that given location. What are these rings due to? It's not clear. Some people claim that this is a property of the disk, that its density is not a smooth power law function with distance. Other people claim that these rings appear when planets start to appear. In either way, rings may be helpful in preserving dust on long time scales, and so that then the gas starts to go away, the dust remains, and the dust to gas ratio can increase and exceed again the threshold to trigger the streaming instability. So for instance, one could imagine that at the snow line where the first planetesimals form, rapidly a planet forms, this planet becomes massive enough, and then it starts to create these rings. The moment it creates the rings, the dust is trapped in the rings and cannot disappear anymore. So we don't get this depletion that we observe in the Darskowska and Dalibert simulation that don't account for the formation of rings. So this is a possibility. Another possibility is that the first generation of planetesimals, wherever they are, at some point start to collide with each other. Maybe when the gas starts to go away, and so the damping that the gas exerts on the planetesimals weakens. And so the planetesimals can start to have mutual collisions at high velocity, and this produces debris. And debris can be dust particles. And indeed, we see around many young stars debris disks. So these are disks with a very high dust to gas ratio that are believed to be generated by the mutual collisions of an already formed generation of planetesimals. And this is also a possibility. At the end, this issue of whether dust is preserved or is regenerated boils down to a question, an unsolved question in planetary science, which is what is the origin of chondrules? So chondrules are the major constituents of chondrites, which are the second generation planetesimals that form 2 to 3 million years after CI times. And there are essentially two clumps, two camps in the community about the origin of chondrules. For some, chondrules are simply dust grains that have been preserved in the disk somehow. And at some point, these dust grains have been molten due to some disk heating events. And so by becoming molten and then crystallizing again, they form the particles, solid particles with the structure that corresponds to chondrules. According to the other camp, the chondrules are the outcome of energetic planetesimal collisions that eject vaporized rock or liquefied rock, and then this vapor or liquid then recondenses or recrystallizes, and this forms chondrules. So in this case, chondrules would be the debris of these debris disks, and once they are generated and most of the gas is going away, then locally at least the dust to gas ratio, the chondrule to gas ratio can become large enough to form the second generation planetesimals, namely the chondrites. But we don't really know which one is true. So if the dust is preserved and then heated to make the chondrules, or if the dust goes away and it's regenerated in the collisions and the collisions makes the chondrules directly. So from our ignorance about planetesimal formation, we can now try to build the second step of solar system formation, which is the formation of the planets, or at least the protoplanets. So going from the planetesimals to the protoplanets. And here there are two processes which have been envisioned, both of which have to work at some extent. The first one is that once you have a disk or a ring of planetesimals, well, these planetesimals will collide with each other. And by colliding with each other, if their relative velocity is small enough, because they are already relatively big, remember, several kilometers, maybe hundreds of kilometers, their common gravity is non-negligible, so they can stick if they come together slowly enough. And by this process, bigger and bigger bodies can be built, and once a body is bigger, it attracts more easily the other planetesimals because its gravity is bigger. So this is the process called runaway growth. It's like in economy, when person is rich, can invest and get more money, become richer and richer. And this is what is happening in our society, as we know very well. And so this process is envisioned to happen in a planetesimal disk, forming protoplanets or planetary bodies. The other idea is that the largest planetesimals, maybe those that started to grow by this process, at some point start to accrete individual dust particles as they drift in the disk due to gas drag. And then the planetesimals can capture a good fraction of these drifting grains and become bigger and bigger by accreting grains over grain. And this process is dubbed pebble accretion. So pebble accretion has two advantages over planetesimal collisions. The first one is that there is no isolation. If a body, if a protoplanet grows by accreting planetesimals, once it has accreted planetesimals throughout its neighborhood, it's over. the disk becomes empty and the planet and the body cannot grow any further because planetesimals are fixed in the disk. They don't migrate very much. They are quite immune from gas drag. But if the body accretes pebbles, this problem of isolation doesn't exist because the particles drift radially in the disk. So even when the growing planet has captured all the dust particles in its vicinity, new dust particles will come and refill its vicinity. Only when the planet becomes very, very, very massive, above 20 Earth masses, there are gravitational effects that can stop the dust, the flux of dust, as I will show later. So this is the first advantage, no isolation, because of the drift of dust and not the drift of planetesimals. The second advantage is that the accretion cross-section for a dust particle is bigger than for another planetesimal. So look at this result of this simulation from Lambert and Johansen 2012. Here we have a planetesimal, the body, the star tries to accrete other solid material. And here we have two particles coming in, as you can see, relative to this accreting body. They come in with the same velocity and the same impact parameter. But of these two particles, one, the black one, is another planetesimal, and the red one is a pebble, a small grain. So the planetesimals trajectory is deflected by the gravity of the accreting body. So the trajectory is not like this, it's bended. But in this case, there is a miss, and this planetesimals is not accreted by the central planetesimals and goes away on a deflected orbit. The dust particle is also deflected in the same manner, but because the dust particle, the pebble, is strongly affected by gas drag, it loses its energy, its binding energy with this accreting body and spirals down. It's eventually accreted by the accreting body. So clearly, for the dust particle, this impact parameter is an accretional impact parameter, whereas for the other planetesimals, this impact parameter, which is the same, is a non-accretional impact parameter. In order to have a planetesimal collision, the impact parameter, this planetesimal, should come down at a with a much smaller impact parameter. So the accretional cross-section is larger for dust than for planetesimals. So this favors pebble accretion over planetesimal accretion. Of course, to be effective, or for pebble accretion to be effective, the flux of pebbles has to be large enough. If there are no pebbles in the disk, then pebble accretion is not very effective. But if this is the case, it has been shown, for instance, in Lambrecht et al. 2014, that the cores of giant planets, so these 10, 20 Earth mass solid bodies that we think are at the basis of the formation of giant planets, can form within the lifetime of the disk, whereas it's maybe difficult to understand the formation of protoplanets so big, 10, 20 Earth masses at 5, 10 AU, solely by the mutual collisions of planetesimals. So pebble accretion is somewhat preferred, even if some authors still prefer planetesimal accretion. And for instance, if you hear a lecture by Jan Aliber, he will argue quite strongly in favor of planetesimal accretion. And for some extent, probably the two work together in order to form protoplanets. My preference is that, at least for the cores of the giant planets, pebble accretion played a role. But I would like to make 2 points here. First is that when independently of how planets form, during the disk lifetime, so when they're still embedded in the gas, they must be subject to orbital migration. So what is that? So look at this animation from Frédéric Massé. Okay, so we stop it for a second. So this is a planet embedded in a disk. The sun is here, and the colors represent the density of gas. There's no dust here. So orange colors means a certain density of gas, darker color means less gas, brighter colors means more gas. The planet perturbs the gas and launches a spiral density wave. And what we see in this animation is the motion of the planet in a reference frame that is co-rotating with the planet around the star. So we don't see the planet turning around the star. It stays fixed for your convenience. And as time goes on, we see that it drifts towards the star. So it migrates through the disk towards the star. And in this specific simulation, the planet is growing as it migrates. And here, this Cartesian plots projects the location of the planet as a function of time so that we can see the migration speed. So let's continue the simulation. So we see that the planet migrates closer and closer to the star. It accelerates because it becomes more massive. But then at some point, it becomes so massive that it opens a gap in the gas of around the disk, and this slows down the planet because it changes the migration regime from what we call the type 1 regime to the type 2 regime. And the type 2 regime, the type 1 regime migration is proportional to the planetary mass. In the type 2 regime, migration depends mostly only on the viscosity of the disk. So migration is a fact. I mean, it's a principle of fundamental physics, and there is no doubt that planets have to migrate when they become massive enough in a protoplanetary disk. So this raises first question: how is it possible that our giant planets that form massive within the lifetime of the gas are so far out? If they migrate towards the star, why is Jupiter at 5 AU, Saturn 9, Uranus and Neptune even beyond? So a first order solution is that maybe they started to form a very large distance, 15, 20 U, they migrated down, and by the time the disks disappeared, well, they reached their current location. This is the position, for instance, taken by Beach et al. I think this is problematic because one has to remember that the privileged location to form early planetesimals and hence a massive planet is the snow line. For the moment, it's the only place where we can understand planetesimal formation. Probably planetesimals form also elsewhere for some reason we did not understand yet, but it's undoubted that the snow line plays a privileged role. So the first big core should form the snow line. And the snow line in an early disk should be 5, 7, maybe 10 AU. So not so far from the current location of Jupiter. So Jupiter must have had a reduced migration. And how? So the other idea is that Jupiter maybe grew very quickly to a mass capable of opening a gap in the disk. And then the disk had a very small viscosity, and therefore the migration of Jupiter once opening a gap in the disk was extremely small. And how this scenario is realistic is under exploration. For the solar system, though, I would like to point out that Jupiter is not alone. Jupiter is accompanied by Saturn, and it has been shown already in 2001 in other works, subsequent work, that the coexistence of Jupiter and Saturn in the disk changes the migration pattern by a lot. So if you put Jupiter and Saturn in a disk, what happens is that in a random location, Jupiter somewhere, Saturn further out, is that initially Jupiter migrates towards the star, the sun, so it's a semi-major axis, whatever normalized units, decreases over time. And Saturn does the same. It migrates towards the star, and it migrates faster because the gap opened by Saturn is not as clean as the gap opened by Jupiter. So the migration of Saturn is an hybrid between type 1 and type 2 migration. So Saturn migrating closer to the sun, towards the sun, approaches Jupiter. And eventually, it approaches enough to be captured in a mean motion resonance with Jupiter. Typically, the 3-2 resonance can also be the 2-1 under some conditions. Typically, the 3-2 resonance occurs when the period of Saturn is 1.5 times, 3/2 the orbital period of Jupiter. And when this happens, you see that the migration of Jupiter stops, and so also the migration of Saturn stops, and the planets slightly migrate out. So this is what happens in a warm disk. If the disk is even warmer, maybe the migration keeps being inward, but very, very slow. And if the disk is cold, then this outward migration becomes more pronounced, and really the migration reverses, and both Jupiter and Saturn start to migrate outwards. So we don't know in which regime was the protoplanetary disk in the solar system, if Jupiter was slowed down, it stopped, the migration reversed. But clearly, as soon as Saturn formed, it must have played a role in keeping Jupiter and preventing Jupiter from migrating too much. We don't know how typical this is in extrasolar planet giant systems, but for the solar system, this should have played a role. The second point I would like to make is that we have empirical evidence that at least Uranus and Neptune did not form solely by pebble accretion. Maybe the cores of Jupiter and Saturn did, but not Uranus and Neptune. Why do I say that? Because if we look at the spin axis of the giant planets, we see that Jupiter has a vertical spin axis, whereas Uranus and Neptune are very inclined spin axis. For Neptune, the inclination is 30 degrees. For Uranus, is even 98 degrees. Now, if Uranus and Neptune had accreted only pebbles, then their spin axis should have been perfectly vertical. So the fact that the spin axes of Uranus and Neptune are not vertical is a strong indication that these planets suffered giant impacts, because the community has never found any other dynamical process that can change the orientation of the spin axis of these planets. You see that also Saturn is tilted by 26 degrees, but for Saturn there is a dynamical explanation, a complicated one. It's called the spin orbiter resonance. I will not enter into that. Don't need any fancy collision, nothing. The change in obliquity of Saturn is well understood, but those of Uranus and Neptune not. So it really seems that giant impacts are the only option. So that means that maybe by pebbles, some protoplanets of intermediate mass grew, but then these protoplanets had to collide with each other in order to form Uranus and Neptune. How could this happen? I think that this is the result of the interplay between the migration of these protoplanets, which were smaller, fewer masses, maybe 5, 6 of masses and larger in number, and Jupiter and Saturn, that because of their gravitational interplay, were not migrating in the disk, or were migrating out, or slowly in, we don't know. So here we show a simulation from this paper from Isidoro, myself, and others, showing how the formation of Uranus and Neptune might have happened. So here we postulate that Jupiter and Saturn are already fully formed. We assume that they don't migrate for simplicity. If they move slowly inwards or slowly outwards, it doesn't matter. Beyond them, there are a number of super Earth planets, 5 Earth masses. The colors represent the mass of these planets. And we are still embedded in the disk of gas. And now we will show the evolution of this system with respect to the 7 major axes of their orbits, their distance from the sun, and the orbital eccentricity. I remind you, because we show several simulations in this kind of coordinates, that the orbital eccentricity is the shape of the orbit. The star is always in the focus of the ellipse. So if the orbit is circular, the eccentricity is 0, the orbit is circular. If the eccentricity grows, the orbit becomes more and more flattened, elliptic, and elongated on one side, with a small perihelion distance and a large aphelion distance. So let's see what happens. So these bodies would like to migrate towards the star, but Jupiter and Saturn are on their way, and they prevent them to go towards the sun. And the bodies are captured in resonances with Saturn. And because there are too many, there is not enough space for everybody. So they have to collide with each other, and they can form a system with smaller planets and larger masses. Here we have for the moment 4 planets, but this is still an unstable system. And after some instability that we will see in a sec, this system of 4 planets will end up to form a system of 2 planets. And if you look at the colors, these 2 planets have typically 15 Earth masses. So we have 2 planets with the masses comparable of Uranus and Neptune forming behind Jupiter and Saturn, and forming via a series of giant impacts among protoplanets of several Earth masses. So no doubt that the spin axis of planets formed in this way would be randomly oriented, as the spin axis of Uranus and Neptune are. We show now another simulation starting from basically the same initial conditions. Now we put a little bit of mass spread among these super Earths and see what happens, just to illustrate that when you have this kind of dynamics going on, the system is chaotic. So there is a strong sensitivity on the initial conditions. So the evolution is similar, but different. And in this case, for instance, it will converge to the formation of not 2 planets of the mass of Uranus or Neptune, but 3. And you will understand later why I showed this simulation. So having said all of this, so clearly pebble accretion is thought to be a very important effect, so forming the cores of Jupiter and Saturn very quickly, forming these protoplanets eventually colliding and forming Uranus and Neptune. There is a natural question you should ask yourself. Why these big planets of 10 Earth masses, like the cores of Jupiter and Saturn, or several Earth masses, like the precursors of Uranus or Neptune, formed only in the outer solar system, and in the inner solar system, the planets form much smaller, at most 1 Earth mass. Why could that be? In principle, accretion is privileged closer to the sun because the orbital time scale, which is basically the clock of any dynamical process, becomes shorter. So also accretion should become faster. So the idea that we have proposed is that this is due to the different size of grains beyond the snow line and within the snow line. As I said repeatedly, within the snow line, the disk is hot, only silicates, refractory material are solid, and these particles should only form at most millimeter-sized grains. Beyond the snow line, these refractory particles combine with the ice, and because the ice is more sticky, we can envision to form bigger pebbles, centimeters, maybe decimeter size, which are made of refractory particles entrained in an icy matrix. As this body migrates and passes the snow line, as I said before, the ice sublimates, this aggregates is dispersed, and the smaller silicate particles, smaller refractory particles are released. So there can be a contrasting size between the pebbles beyond the snow line and within the snow lines, a contrasting size which can be 1 or 2 orders of magnitude. And pebble accretion is very sensitive on the size of the pebbles. So for instance, you can imagine that you have 2 protoplanets of the same mass. So for instance, here half of the lunar mass, one inside of the snow line, one outside of the snow line, the green and the red one. And because the red one sees a flux of big pebbles, whereas the green one sees a flux of smaller pebbles, then in the time the red one grows to 20 Earth masses, the green one, because it can only feed from smaller particles, grows only to Mars mass. Of course, this mass ratio depends on the numbers I put, right? If the pebble size ratio is smaller, it will be less. If the pebble size ratio is bigger, it will be bigger. In addition, nothing tells us that the precursors had the same mass within the snow line and beyond the snow line. That depends on the planetesimals that form. And as I said before, we don't understand planetesimal formation within the snow line. So we really don't know. But there are a number of parameters on which we can play and that can explain, at least in a qualitative manner, why, despite the orbital periods are shorter, closer to the sun, accretion proceeds faster beyond the snow line than within the snow line. Bigger pebbles and maybe also bigger seeds. Okay, and once the outer body, so the body growing fast, reaches a mass of 20 Earth masses, the drift of particles from the outer disk to the inner disk stops at the orbit of this 20 Earth mass planet. Why is that? Because when a planet becomes big enough, as I said, it starts to open a gap. And even a shallow gap has a profound effect on dust dynamics. So this plot shows the surface density of the gas of the disk sculpted by a planet of 30 Earth masses. So this is the radial coordinate, so pointing towards the star. This is the azimuthal coordinate going around the star. The planet is placed here, and as I said, launches a spiral density wave. It opens also a shallow gap, so this region where the color is blue means less gas. And by opening these gaps, it creates an overdensity of gas here in this band, which is bright green. Now, because of the change in the distribution of gas induced by the presence of the planet, the rotational properties of the gas change. And this is shown in this right plot. So here, the vertical axis is the same as here. And here, what I plot is the ratio between the orbital velocity of the gas in the azimuthal direction and the Keplerian velocity. So when the rotation of the gas is equal to the Keplerian velocity, that this ratio is 1, and 1 is located here. So as you can see, far away from the planet, closer to the star, or far away from the star, the ratio of orbital velocity to the gas, the Keplerian velocity, is always smaller than 1, which means that the gas turns around the star slower than the Keplerian motion. So the gas is sub-Keplerian. The dust tends to move at the Keplerian speed. So because the gas is moving more slowly, it feels a headwind from the gas, and this drags the particle, makes the particle lose energy and momentum, and therefore the particle moves spiral towards the sun, migrate towards the sun. But close to the orbit of the planet, as you can see, this ratio becomes a mess. And in particular, just outside of the orbit of the planet, here in correspondence of this bright green band, which I remind you is an overdensity in the distribution of gas in the disk, you see that the orbital velocity of the gas can become super Keplerian. The ratio can exceed 1 as soon as the planet exceeds 20 Earth masses, and this ratio becomes bigger and bigger if the planet is more massive. So what happens? Imagine to have a pebble here. It's in the outer disk. So it sees a sub-Keplerian disk, which slows the particle down and forces it to migrate inwards. So it migrates inwards, but when it comes here, it reaches a point where the disk turns from being sub-Keplerian to super-Keplerian. So the headwind becomes a tailwind and pushes the particle out. So this is an equilibrium point, if we refer to the magenta curve, where the dust particle has to stop. The particle cannot go further, cannot cross the orbit of the planet, cannot go in the inner disk. So the dust piles up outside of the orbit of the planet, and the inner disk remains starving. It's not fed by new particles coming in from the outer part of the disk. And so that means that any other planet that is growing in the inner disk by pebble accretion stops. There are no more pebbles coming in. So we think this is what happens and what we see in many extrasolar disks. Indeed, very often we see what we call transition disks. These are disks that have a lot of dust in the outer part and a cavity in the dust, not in the gas, but in the dust in the inner part. And the interpretation is that there is some giant planets, some planets of at least more than 20 Earth masses, doing what I just explained. So the dust has to remain beyond the orbit of the planet and cannot go inside. So the region of the disk inside the orbit of the planet becomes progressively depleted in dust because it's not refed by the dust migrating from the outer disk, and becomes more and more clear and forms this inner cavity. So this, we think, has been invoked at least to explain this dichotomy in the isotopic composition of meteorites. The fact that the solar system had initially two different compositions in the inner part and the outer part, well, for some reason, but that this dichotomy did not go away with time as a result of particles on the outer disk drifting into the inner disk. So the idea is that Jupiter grew fast enough to above 20 Earth masses. Of course it did, because at the end it's 300 Earth masses. What we don't know at what time, for instance, it exceeded 20 Earth mass. But the proposal is that it exceeded 20 Earth masses quickly enough, maybe just a few 100,000 years, to stop this dust flux from the outer disk into the inner disk. So the inner disk was not contaminated by the outer disk and preserved its distinct isotopic composition. This is the proposition made by Carrier et al. 2017. Okay, so now let's come to the formation of the terrestrial planet. So everything I discussed so far happens in the disk of gas. And remember that we know from chronological constraints that the Earth, at least, completed its formation much beyond the time scale of gas survival. So how terrestrial planets could form? So given the predominance of pebble accretion for the formation of the cores of the giant planets, the natural idea is that, well, maybe also the terrestrial planets formed by pebble accretion, less fast because pebbles were smaller, seeds were smaller, and so on. So maybe they grew by pebble accretion to just to the mass of Earth and Venus, maybe just a little bit less than the mass of the Earth, because there was this protolunar impact at the end, so 90% of the mass of the Earth, let's say. Is this a possibility? Well, I think it's not a reasonable possibility, because if the bodies grow within the lifetime of the disk, so as long as the pebble accretion, understood, can happen only when there is gas, because you need gas friction to move the pebbles around. So if planets grow bigger the mass of Mars in a disk of gas, they start to migrate efficiently in the disk, and migration is mass dependent. So how can you get this structure of the terrestrial planet system with two small planets on the periphery and the two major planets at the center? The Earth and Venus, if they grew to their masses within the gas disk, should have started to migrate inwards, as shown in Ambrish et al., and approach the inner edge of the disk, maybe dragging along in resonance Mercury, but forming a large gap distance with Mars, because Mars doesn't migrate as efficiently. So the orbital characteristics, the orbital mass characteristics of the terrestrial planets are really hard to reproduce using pebble accretion. So maybe then one could think, okay, it's not the terrestrial planets that grew by pebble accretions, but only intermediate objects that we can call planetary embryos that grew up to the mass of Mars by pebble accretion. This cosmochemistry, from the point of view of cosmochemistry chronology, would work, because we've seen that Mars grows on a time scale comparable to the disk lifetime, 4 or 5 million years. But even this, it's unlikely, because as I showed in the first part of my lecture, using this dichotomy in isotopes, one can constrain that even Mars accreted less than 5% of its mass from carbonaceous material coming from the outer disk. So the contribution of dust coming from the outer disk, they sort of limits, gives an upper bound to the amount of mass accreted by pebble accretion, is really very small. So I do think, not everybody agrees with me, but I think these arguments are very strong, that the classic model for terrestrial planet formation, which was envisioned well before pebble accretion was designed, is much more appealing. So what is this classic model about? Classic model was introduced by this scientist, which I really wish to pay tribute to, George Wetherill, who envisioned the formation of terrestrial planets happen in 2 steps. First, the first step within the lifetime of the gas in the disk is that the disk of planetesimals, by mutual collisions, formed protoplanets, planetary embryos of about the mass of Mars. And this process works. You don't need any pebble accretion, just mutual collisions doing it. These are borrowed 2 plots from a very recent work from Walsh and Levison last year. And this shows the growth of these planetary embryos, the black dots here, from disk of planetesimals. The bottom panel shows the radius of the particles or the bodies as a function of their heliocentric distance at 3 time snapshots, 1, 2, 10 million years, once the gas is totally gone. And the top shows the eccentricity. Okay. And as you can see, from a disk of planetesimals, initially they're only planetesimals, a set of planetary embryos grows, and then as time passes, these planetary embryos grow a little bit further, typically stall at a mass comparable to the mass of Mars, and the population of these planetary embryos extends further and further out in heliocentric distance. And here you see the typical mass of an embryo as a function of time as 1 AU. In black was the results of older work by Chambers 2006. In color is the result of these more refined simulations, which are certainly more sophisticated, but as you can see, the result is about the same. So starting from planetesimals, within the lifetime of the gas, say 1 million years, one can form protoplanets, planetary embryos of a typical mass of the mass of Mars, and one forms many of them. Okay, so clearly this is not the final terrestrial planets. One then needs a second step. And Wetherill envisioned that the second step occurred after the disappearance of gas from the disk. The gas keeps embryos and planetesimals damped, so quite circular coplanar orbits that don't collide very much with each other. But once the gas goes away, then the system can get very excited by mutual encounters, mutual collisions, and the perturbation from Jupiter, which is fully formed by the time the gas goes away. And then the dynamics of the system has a drastic change. We show that from these simulations taken from this paper by O'Brien et al., but there have been a number of numerical modeling of this process, all showing about the same thing. So again, the coordinates are the same major axis and eccentricity, which I explained before. The small green dots are the planetesimals. The red big dots are the embryos. And as we will see the embryos growing towards planets, we will see them becoming bigger because the size of these dots is proportional to the radius of these planets. This is Jupiter, already fully formed, and these dashed lines show the boundaries of the asteroid belt, just for reference. So let's see what happens. As time goes on, this is now time not from CI formation, this is time from gas removal. So we already have our set of embryos embedded in the disk of planetesimals. So as time goes on, very quickly, the system stirs up, and stirs up in particular in the region of the asteroid belt because of the perturbations from Jupiter. So all the embryos go away, together with a lot of planetesimals go away from the asteroid belt. But in the terrestrial planets regions, the embryos don't go away, and they keep colliding with each other, so growing in mass, until their numbers become smaller and smaller, and eventually a stable planetary system is formed. In this case, a system of 3 terrestrial planets, but in some cases it can be 2 or 4 or 5. Again, due to the intrinsic chaoticity of these kind of simulations. And you see that then once the planets are formed, as time goes on, because of the interaction of the planets with the leftover planetesimals, the eccentricities of the planets are finally damped. And so a fairly circular system is produced in the end. And indeed, the terrestrial planet system is in first approximation on quasi-circular orbits. So this kind of model envisioned by Weather, it works very well. It can explain many, many things. It explains the formation of few terrestrial planets from 2 to 5 in the terrestrial planet region. And typically there are no planets forming in the asteroid belt in most simulations because of the strong dynamical perturbations from Jupiter. Typically the most massive planets are of the order of the mass of the Earth. The orbits are quite good, with small eccentricities, small inclinations, particularly if one uses many planetesimals. The accretion time scales for the Earth is about right. It takes tens of millions of years for this, for accretion to take place. And if you remember the first part of my lecture, this is the typical time scale for the accretion of the Earth according to radioactive chronometers. And giant impacts are typical because planets grow by accreting planetesimals, but mostly grow by collisions with other embryos. And we know that at least one giant impact happened on Earth, is the one that is supposed to be responsible for the formation of the moon. Here I show a simulation from Willy Benz, which I forgot to acknowledge here. Sorry for that, Willy. And this collision generates a disk of debris around the Earth in vapor and solid form. And from this disk of debris, then the moon can form. And so because the planets form via a sequence of these giant impacts, then it's not outrageous or very unlikely that one giant impact happens at the very end and forming the moon that we know. And also some water-rich bodies from the asteroid belt or beyond Jupiter can come to the Earth, delivering the water which characterizes our habitable planet. However, there is one big problem. If one does many of these simulations, and at the end, one plots the mass distribution of the planets obtained in the simulation, so the mass of the planets obtained in the simulation as a function of their final location, one finds a distribution of this kind that we can compare to the real masses of the terrestrial planets. And here you find that although the simulations reproduce fairly well the mass of the Earth and Venus, the planets that typically form at the location of Mars are much bigger than Mars. And this is not right. Mars is smaller, and Mars stopped growing much faster. So the growth of Mars was aborted somehow. And this is not what we see in this kind of simulations. Something else is needed. And this problem received a solution or thanks to Brad Hansen in 2009. Brad showed that if instead of starting from an extended disk of planetesimals and embryos like the one I showed before, one starts from a narrow ring of embryos and planetesimals located from between 0.7 and 1 AU, so a really narrow ring with about 2 Earth masses of it in it. Then from these initial conditions, running simulations like those I showed before, one gets a distribution of planetesimals in the various simulations. Here are many, so many simulations all plotted together, but this pattern reproduces very well that of the real planets with small Mercury and the small Mars and big Earth and Venus. Fantastic. But now the question is why the solid material, planetesimals and embryos, were concentrated in such a narrow ring? And here, all bets are off. So there are two possibilities. The first possibility is that this is just a consequence of how planetesimals form. I talked to you before that we don't understand planetesimal formation. So clearly planetesimals form at the snow line, but they have to form somewhere also in the inner system because we have early planetesimal formation at least at two distinctive sites. Once we will be able to solve that, maybe we will find out that there is already a narrow range around 1 AU and early planetesimals can form. So early planetesimal may form in a narrow range around 1 AU, then in a more or less a narrow range close to the snow line, and very unlikely to form in between. So there is a gap. And then, because of this ring, we produce the terrestrial planet system that we see. The planetesimals at the snow line from the cores of the giant planets that grow. And then the giant planets scatter the planetesimals around them, and some are injected in the asteroid belt. The few local planetesimals remain in the asteroid belt. And at the end, we have a low mass asteroid belt, which is made of two distinct planetesimals types, those that form in the inner system, say non-carbonaceous, and those that formed beyond the snow line and scattered inward by the giant planets, which are the carbonaceous ones. So this is a possibility. We don't know if it's right or not because we don't understand planetesimal formation, so we cannot assess whether or not planetesimal formation would produce such a narrow ring that's needed in order to create the Mercury, Earth, Mars, Venus, Earth, Mars mass distribution. The other possibility is that no, the disk of planetesimals was continuous. There was no gap between the inner part and the Jupiter region, but some dynamical process depleted very rapidly the disk beyond 1 AU, from 1 AU to Jupiter's location. And two of these processes have been proposed. One is based on the migration of the giant planets. So as I showed you before, Jupiter initially tend to migrate inwards, but once Saturn shows up and captures Jupiter in resonance, if the disk is cold enough, migration is reversed. So in 2011, Walsh et al. Postulated that maybe Jupiter migrated down to 1.5 AU before being pulled back by Saturn. And then, of course, the inward followed by the outward migration of Jupiter and Saturn created a big hole here. So leaving Mars stunned in a region with very little mass, and leaving behind just a very low mass asteroid belt, again made of planetesimals that were local planetesimals scattered outward and back inwards, and outer these planetesimals scattered inwards. The other possibility is that the giant planets became unstable, so their eccentricity increased, and this perturbed the asteroid belt region, removing most of its mass, leaving behind again an asteroid belt which has low mass and comprised of two populations of planetesimals damped in the same region. And this also stunned the mass of Mars. And this has been proposed by Matt Clement in a number of papers, mostly in 2018 and 2019. We don't know. We don't know of these three scenarios, which one is the most correct. And so research is still active in trying to take these scenarios apart and show which one is most reasonable. But what is this business of giant planet instability invoked by Clement et al.? And this is the last step of solar system evolution, I would say. Why do we need an instability in the solar system? Well, you remember the simulations I showed about the formation of Uranus and Neptune after the formation of Jupiter and Saturn. So the protoplanets, the precursors of Uranus and Neptune, migrated closer to Jupiter and Saturn, were trapped in resonance with Saturn, and collided with each other to produce Uranus and Neptune. The final system had these characteristics. This is the outcome of the first of the two simulations I showed before about the formation of Uranus and Neptune, and has the two planets, Uranus and Neptune, here very close to Jupiter and Saturn. The full giant planet system was comprised between 5 AU and 12 AU. And this is very different from the solar giant planet system we know today. The giant planet system that we know today has much more separated orbits. Jupiter is at 5, but Neptune is at 30, and Uranus is at 20, and Saturn is at 10. And there are no orbital mean motion resonances among the planets, unlike what we get at the end of the gas disk phase. So unless we didn't understand anything about what happens in the gas disk phase, we need a process that is capable of changing these orbits into the current orbits once the gas has disappeared. And we think that this process is due to a dynamical instability. Dynamical instability triggered by the mutual interactions of the planets and the interaction of these planets with a trans-Neptunian disk. And this is the basis of the NIS model. There are many versions of the NIS model, and here I show the latest. So as time passes, the planets stir the planetesimal disks, and the planetesimal disk perturbs the planets. And after some time, and this simulation is very long, so you can have time to speak. The time depends on the separation between Neptune and the inner edge of the disk. It can be short or long, depending if the separation is short, is small or large. After some time, the planetary system becomes unstable. Then the planets become eccentric, they have close encounters with each other, they spread around. Uranus and Neptune are tossed out, they disperse this planetesimal disk. A result of the planetesimal dispersion, their eccentricities and inclinations are redamped close to zero. Only Jupiter and Saturn remain partially eccentric and inclined behind. As you can see, at the end, we have Jupiter at 5, Saturn at 9, Uranus at 20, Neptune at 30. So it's about the real orbits of the planets. The dynamical instability is needed to reconcile the orbits that the planets should have had during the gas disk phase because of migration with the current orbits that they have. And indeed, if one studies in detail the evolution of the planets and the instability, one finds that actually the best reproduction of the orbits, the current orbit of the giant planets, is obtained if at the beginning there were 5 planets, Jupiter and Saturn, and 3 planets with the masses of Uranus and Neptune, and 1 was ejected and 2 survived. Because in this case, one gets a bigger kick to Jupiter and Saturn. And you will see the model again is 0 is the time of the instability when the planet becomes very elliptic and ejected. So the encounter of this ejected planet with Uranus and Neptune with Jupiter and Saturn, can really give to Jupiter and Saturn the eccentricities that we see. Instead, if we have 4 planets at the beginning and 4 planets at the end, the gravitational interaction has to be weaker to preserve the 2 smaller planets, and Jupiter and Saturn at the end are not eccentric enough. But as I showed before, that was my second simulation. That's why I showed it. In this process of formation of Uranus and Neptune, sometimes you form 2 planets, sometimes you form 3 planets. So postulating a 3rd planet with a mass comparable to Uranus and Neptune is not crazy. And this indeed was already proposed in the past, in 2011, as Zvorny, Batygin, 2012, and then was shown to be really the best initial conditions to reproduce the current planetary system. Now, the real smoking gun for this kind of evolution having really occurred in the solar system is that it explains this very complex dynamical structure of the small bodies populations in the outer solar system that I described in the first part of my lecture. So let's start from the Kuiper belt. Remember, the Kuiper belt is made of a cold population and a hot population. And the idea is that the cold population, which is low inclination, low eccentricity even now, is a sort of local, small mass, primordial planetesimal population. And then the hot population is being implanted from this trans-Neptunian planetesimal disk, initially extending only up to 30 AU. The instability which tossed Uranus and Neptune into the disk, dispersed this disk. Most of the planetesimals have been ejected, but about a planetesimal in 1,000 can be trapped in the 40 to 50 astronomical unit region. And because of the strong scattering is suffered from Neptune, the final eccentricity and inclinations are typically larger than those of the cold population. And Zvorny has studied this process in particular detail, and he has found that the eccentricity distribution and inclination distribution of the hot population are really very well matched by the simulations. Here, the dash curve shows, for instance, the cumulative inclination distribution observed in the hot Kuiper belt. And this is what the model predicts once observational biases are correctly taken into account. And the top panel is the same, but for the eccentricity. On top of that, this process derives the hot population and the cold population from two different reservoirs. The cold population was born in situ. The hot population was closer in, was inward of 30 AU, and was tossed out by the instability. So it's conceivable that the hot population and the cold populations are physically different. And you remember that I told you that they have a different size distribution at large sizes. They have a different color distribution, as I highlighted in this cartoon here. Trans-Neptunian region is not just made of the Kuiper belt. There is also the scatter disk and the Oort cloud, but the same process that implants the hot population also produces a scatter disk. So this feature spanning some major axis up to a few thousand AU with a perihelion distance of 30 to 40 AU, and then perturbed by the galactic tide and passing stars and forming the Oort cloud. And indeed, the inclinations are in these two structures, scatter disk and Oort clouds, which form so at the same time from the same reservoir, reproduce what we deduced from the cometary flux. The scatter disk is entirely prograde with inclinations ranging up to 40-50 degrees. The Oort cloud has all possible inclinations from 0 to 180 degrees. Half of the comets are prograde, half of the comets are retrograde. And from the simulation, the population ratio between the Oort cloud and the scatter disk is about 50, which is about what we deduce from the observations of the fluxes of Jupiter family comets and coming from the scatter disk, and long period comets coming from the Oort cloud. So this also works very well. And remember what I told you in the first part of my lecture, the very existence of the Oort cloud, because it's made of small bodies, comet-sized bodies, reveals that these bodies have been dispersed by the planets after the disappearance of the gas to avoid gas drag. And this is exactly what this instability does, because it happens after gas removal. So there is no gas anymore to tempt the bodies, and therefore small particles can go in the Oort cloud and not just the big planetesimals. Let's talk about the irregular satellites. All planets have, giant planets have irregular satellites, and the fact that they're all similar once rescaled by their here radius was suggesting that gravity alone was the process capturing these satellites. Well, during the instabilities, planets can have mutual close encounters. And when they have mutual close encounters, they are embedded in these disks of dispersed planetesimals. And so when encounter happens, some planetesimals can be having encounters with both encountering planets. And so this is a free body dynamics, four body dynamics with the sun. And as a result, these planetesimals, for instance, can be captured around each planet. And when they are captured, their orbits are very eccentric and typically fairly inclined. Now, this is a cartoon, but again, Nesvorny did very detailed simulations to compare the orbital distributions of the planetesimals captured in this process and compare it with the orbital distribution of the real irregular satellites. And this is what you see for Neptune, Saturn, Uranus, and Jupiter. So the red triangles show the real irregular satellite, the small dots, the orbits of the satellites captured in the simulation. The match is perfect. This diagram shows the distribution of irregular satellites in the sine major axis versus eccentricity plot. And this is sine major axis versus inclination plot. So you can see you have the prograde clump with inclinations less than 60 degrees, the retrograde clump with inclinations larger than 130 degrees. And the match is simply stunning for all of the planets. And this is the only process that has been shown so far to reproduce the orbits of the irregular satellites so well. Trojans. There are Trojans around Jupiter and Neptune, not around, but on the orbit of Jupiter and Neptune. And the Trojans in this model are captured when the planets become unstable because their orbit jumps. They are embedded in this sea of dispersed planetesimals. And when the orbit of the planet jumps, some planetesimals all of a sudden can find themselves to be co-orbital of the planet in the new orbital position and remain there forever because they are stable. The idea is nice. Does it work? Again, Nesvorny et al. Did simulations. And here we compare the real distribution of the Trojans, the small dots of Jupiter, in this diagram showing the libration amplitude around the L4, L5 equilibrium point, their orbital inclination or orbital eccentricity. And the open symbols are the distributions of the particles captured as Trojans of Jupiter in 3 different simulations. And as you can see, again, the reproduction of the distribution, orbital distribution, is just stunning. If this model works, it predicts that the Trojans captured even at Jupiter, not just at Neptune. They're coming from the trans-Neptunian disk. So they are brothers and sisters with the hot population. So the hot population went out, was part of the initial trans-Neptunian disk that was scattered out and implanted in the Kuiper belt. Scattered disk and Oort cloud went even further, implanted in the scattered disk and in the Oort cloud. And the Trojans went inwards and they've been captured around the orbit of Jupiter. So they are brothers and sisters. And so Trojans should be physically related to the hot population. I showed in the first part of my lecture that this has been confirmed in terms of size distribution. Size distribution of Trojans and the hot Kuiper belt are indistinguishable statistically and very different from the size distribution of the main belt asteroids. So this is a nice confirmation. But I also said that the color distribution of the Trojans, both at Jupiter and Neptune, are different from those of the hot Kuiper belt. It's just a subset of the color distribution of the Kuiper belt. An idea is that the original trans-Neptunian disk had a gradient of colors with heliocentric distance. And the fact that the Trojans just sampled the less red portion of the hot population suggests that the disk color gradient went from less red to more red, from closer to Neptune to further away from the sun. And the fact that the Trojans are only not very red means that tells you how far out the trans-Neptunian disk was destabilized at the moment that Trojan capture occurred. And Svorny figured out, for instance, a possible gradient of colors with heliocentric distance that does reproduce the color distributions of the Trojans of Jupiter and Neptune from this initial disk. And finally, remember that the Trojans have this color spectrum typical of D-type asteroids. The simulations of the instability show that trans-Neptunian objects are not only implanted in the Trojan region, but also in the 2 to 3 resonance with Jupiter and also in somewhere in the asteroid belt. So all D-type asteroids that we see scattered around in the asteroid belt are probably parented to the Trojans, so parented to the hot Kuiper belt. So they are captured trans-Neptunian objects in the asteroid belt, which is very exciting and allows to make in situ studies with space missions without having to go as far as 40 AU, which of course is very costly and time consuming. Now I've passed very quickly on all of this, but Nesvorny, who you might have understood, did really all these studies in detail, wrote a beautiful and a very exhaustive review about the instability of the giant planets and everything that this allows to reproduce. And so I warmly recommend you to read this review paper. So when did the instability happen? So we are very confident that instability happened because no other dynamical process can explain the distribution of the small bodies in the outer solar system as well. But when the instability happened, it's really unclear. We cannot say a priori because, as I said, when the movies were running, the time of the instability depends on the distance between the initial orbital location of Neptune and the inner edge of the planetesimal disk. And this is unknown. So I can get early instabilities or late instabilities depending on how I put down my initial conditions. So a priori, we cannot give an answer. Initially, it was thought that this instability occurred late. Why? Because it was believed that most of the craters on the moon and the so-called lunar basins, the biggest impact structures, formed late, 700 million years after moon formation. And arguing then that there was a surge in the bombardment of the terrestrial planets. And the way to understand this surge was to postulate that this instability occurred late, at the time of the late heavy bombardment, 700 million years, more or less 600, 700 million years after the formation of the solar system, so about 3.9 billion years ago. But the evidence for this surge in the impact rate, and it is called the lunar terminal cataclysm, or late heavy bombardment, is becoming weaker and weaker with better analysis of the lunar samples and lunar meteorites. And indeed, we also showed that the last obstacles in explaining the lunar crater record with an early instability can be solved. So there are now we don't need to postulate. We can explain the existence of late craters even with a giant planet instability that occurred early and the bombardment that was declining monotonically with time. And from the dynamical point of view, as I said, both early and late instabilities are possible. But if you study the problem more in depth, you find out that the late instability makes more problem than it solves. It's not excluded, but it's more problematic. And the final smoking gun came from Nesvorn et al., who studied the preservation of trans-Neptunian binaries in a trans-Neptunian disk. There are binaries that survive in the hot population. There are even binaries captured as Trojans of Jupiter, Patroclus and Menelaus, for instance. So that means that by the time the instability happened, the trans-Neptunian disk still had a lot of binaries. And binaries tend to be destroyed by mutual collisions. And so Nesvorny showed that if the trans-Neptunian disk lasted for more than 100 million years, it's unlikely that binaries would have survived. So the fact that binaries survived and we can still see them among the Trojans and the hot population argues that the instability occurred earlier than 100 million years. But could it really have happened as soon as the gas went away in the first few million years, as needed to explain the small mass of Mars in the model developed by Matt Clement et al.? This is unclear. My personal opinion is that the instability likely happened the time intermediate from 0 to 100 million years, probably around 50, 60 million years. It's probably associated with the moon forming event, but that's just my personal opinion, and more work is needed about that. So in conclusions, now we come at the end of these two long parts of this lecture. So of the various steps of solar system formation and evolution, as you have understood, the last one is the one we are most confident of. It's the one related to the giant planet instability. Why is that? Not because people who study the giant planet instabilities are better than the other planetary scientists. It's because it's the last step. So we can use strongly the constraints provided by the current distribution of planets and small bodies in the current solar system. It's the last step, so it's the easier to reconstruct. Also, the physics is easier. There is no gas, there is no planet disk interactions, there is no gas drag. It's much easier to simulate. That's why the NIST model was so successful. Despite of that, we still don't know precisely when the giant planet instability occurred, probably in the first 100 million years, but all bets are off. If it happened very early, close to the disk dispersion, the gas disk dispersion, or relatively late, close to 100 million year limit. If you go backward in time, things become more and more mysterious. So the fundamental process of planetesimal formation may be understood. This idea that particles clump in the disk and form self-gravitating clump that then contracts and form planetesimals. I think this is a really great idea and it's a solid one. But we still don't understand how planetesimals form in agreement with cosmochemical constraints, which means forming early planetesimals at least at two distinct sites in the disk, and then forming a later population of planetesimals with basically all over the place, because the instability model requires massive planetesimal disk extending up to 30 AU with a low mass extension up to 45 AU, which is the cold Kuiper belt. And we really don't understand how to preserve dust particles on such a wide range of heliocentric distances in order to produce planetesimals over that such a big range of distances from the sun. This is another big open problem. The origin of chondrules remain mysterious. Chondrules are the main constituents of chondrites, so the second generation of planetesimals. We still don't know if they are just dust grains that remained in the disk and got heated by some unknown process. There are ideas on which process could be, but we're not certain. Or maybe they are debris. And then the second generation of planetesimals is built from debris from the first generation of planetesimals. The actual role of pebble accretion in the formation of giant planet cores compared to planetesimal accretion is still debated. I think pebble accretion played a predominant role and led to the formation of the giant cores of Jupiter and Saturn, but not directly to Uranus and Neptune. And Uranus and Neptune had to go through a phase of giant impacts from precursor protoplanets. But research is still going on this. And how giant planets avoided to migrate into the inner solar system is not fully understood. And this is related to the questions of where did the cores of the giant planets start to form. And finally, which processes confine the material planetesimals and embryos in a narrow ring of the terrestrial planet region, 0.7 to 1 AU, in order to create this nice mass distribution that we see from Mercury to Venus and the Earth and Mars, is still not clear. So there are plenty of things which are not clear. So one can be depressed, but actually you should not, because you are a young scientist who have a future in front of you. And this really means and shows that there are lots of outstanding questions to study. And so the future of theoretically planetary science is bright, and they really encourage you, if you feel capable to engage in this adventure to trying to unveil the how the solar system formed and evolved. So thank you very much for your attention for this very long series of talks. Thank you very much.